Hope you're having a good day. Today, we want to talk about pathogens in wastewater and disinfection. We are in Chapter 7 of Volume 1 of the Sacramento State Programs Edition. I believe it's 8th. And we're talking about wastewater treatment, and it usually removes some pathogens through the following methods. And this is on page 576. The physical removal through sedimentation and filtration. When our primary clarifier, we have the sedimentation and flotation, just from the standpoint that we're removing solids from the system, you're going to have some removal of pathogens. Filtration through a sand filter, you'll have some, but not complete disinfection or sterilization, whatever way we want to talk about it. Another way is a natural die off of microorganisms in an unfavorable environment. The third is this, and what we're mostly going to talk about today is the destruction by chemicals introduced for the treatment purpose process. As you can see on page 577, disinfection is the last thing we do typically before we send it out to the stream. And this is important for the riverways and bodies of water that you're discharging into because people are using them. They're using them for fishing, canoeing. Some municipalities may be using them as drinking water. And so we want to make sure that we are sending out a disinfected product to the receiving waters. Chlorination is one of the most common ways that we use to disinfect and has been for years. But it is a highly toxic substance. It can be toxic to uh, humans at a large level, but it also can be toxic to fish and to wildlife. And as we will talk later on, it is imperative that we dechlor or dechlorinate the water before we send it out to the receiving water. Uh, Chlorine, uh, chlorine is also in the gaseous form. It can be not the safest application, and so sometimes you'll see people go to hypochlorite, which is the liquid form, and that will be on page 578, 579. You'll see that with like a diaphragm pump or a chemical feed pump, a peristaltic pump. A lot of the small plants I used to operate, this is how we would disinfect the wastewater well, water and wastewater is with liquid chlorine. Gas chlorine. When we talk about gas chlorine, we're talking about liquid chlorine as delivered to the wastewater treatment plant in cylinders containing 150 pounds for small plants, or they can be in a 1 ton tank for medium-sized uh, plants. You're going to see this, the 1 ton tanks, in probably your bigger municipalities. And once again, they will use that for cost savings measure because gaseous chlorine is probably a little bit cheaper, um, and that's why they'll use it. Ultraviolet radiation. We use UV at my facility. The nice thing about UV is there's no byproducts that are made. When chlorine reacts with ammonia, you have chloramines. Um, when chlorine reacts with organics, which is the you know, main thing that we're concerned about, is it does create your THAMs and your HA5s, which you're concerned about in your water system. But with ultraviolet radiation, we are zapping it with light. There's no residual disinfection, but uh, it is one way that at least I prefer to treat the wastewater because the EPA is really starting to get stringent with chlorine residuals in the receiving waters. And so it's so low, and they should, it's so low that it's hard to completely remove all that chlorine out. Let's say if you're using a tablet feeder, because that's 1960s, 1970s technology. And unless you are really adept and have a close eye on tablet um, chlorination, it's just it takes a lot of work and a lot of concern to make sure that you are below the detectable limit. Ozonation. Ozone is created when molecules of oxygen are split apart and reformed as O3 molecules. So you'll have an ozone generator that will be at your plant. The reason why we do this is because ozone is not very stable. And so we need to generate ozone at the plant. Chlorine safety program. Everybody should have a written chlorine safety plan if you use chlorine at your plant, especially if you're using gaseous chlorine. People need to be trained. Chlorine is a hazardous gas. It's 2.5 times heavier than air and is extremely toxic in moist atmospheres. You can see the guy on the left almost looks like a fireman, and he's wearing an SCBA. Really, when you're dealing with gaseous chlorine, you really need to be fit tested and wear your SCBA when you're going in to try to diagnose a leak. Um, it can cause severe irritation to the throat, coughing, vomiting, difficult breathing. So, and OSHA has a concentration level that may be fatal at 1,000 parts per million. So, if you work at a facility that deals with chlorine, you need to have a plan. You need to train your employees and know that that chlorine wants to hang low at the bottom of a chlorine room. A lot of plants I've worked at, when you open up the light switch, it turns on a automatic fan at the bottom and opens that up so that any chlorine laden air will be released to the outdoors. And I believe that's a test question that you'll have about where chlorine vents should be labeled. When we talk about chlorine reactions in wastewater, we're talking about free chlorine. We're talking about chlorine demand, chlorine dose, and chlorine reacts with a lot of different things, I've mentioned. And on the chart on 587, that is a good picture of what chlorine does. So first off, chlorine is destroyed by reducing compounds. Then you have the formation of your chloroorganics and your chloramines. They're partially destroyed, and then you get to break point. And when you get to break point, that's really where we want to be, or maybe a little bit um, past breakpoint. When we get to breakpoint, then there's free available chlorine to react with any kind of pathogens or anything in the water. When we do a public water system, the EPA requires that there must be 0.20 residual of free chlorine in the water so that any bacteria can um, be disinfected by that 0.20 residual. For your EPA test, you need to know that chlorine dose equals chlorine demand plus chlorine residual, or it could be said chlorine residual equals combined plus free. So your dose is going to be equal to what your demand is and what residual you want left in the system. Like on the water side, we want a 0.20. So your demand, let's say your demand is a 1 part per million and your residual is a 0.20, then your dose will be 1.20. So just be familiar with that when you're taking your test. When we look at the National Pollution Discharge Elimination System permit, it will give you how many most probable number of coliform group organisms present. And I believe that's off of 100 mils. And so you're only allowed so many E. coli or fecal, depending on your regulatory organization. You're only allowed so many per day of E. coli in to be able to go to the receiving waters. And so you want to know that in your permit. Each permit is going to be different compared to um, what body of water you're discharging into. 594, you can see disinfection. That is a vacuum fed gas chlorinator system. I believe it's using a rotometer. Um, on on page 596, that is an evaporator. That's used where larger quantities of chlorine are going to be used. And so you can see an evaporator is what you would think. It has a heating element. It heats the liquid chlorine up. The gas comes out, and then that gas is what we're going to inject into the wastewater stream, or you water guys and girls into the water plant. So when we're talking about um, reviewing plans and specifications on 599, we want uh, probably six dot down. We want adequate ventilation. It, Adequate ventilation is important in a chlorinator room to remove any leaking chlorine gas. Chlorine rooms should be ventilated using forced ventilation. Exhaust ventilation should be taken from a point 12 inches off the floor. With it being 2.5 times heavier than air, that's where we want to um, take our chlorine laden air out. On page 607, that is a chlorine residual analyzer that goes on the wall at a water facility that I've used. I've used one of those. I don't believe right now that that can be reported to the EPA, but however, it can be wired in conjunction with your SCADA system. So if it drops below, let's say 1 part per million, it can call out and alarm out. You can come in, take a physical test with a meter and take a physical test to verify that. But it's just a good backup control. Um, you know, with chlorine being so toxic to the aquatic life and to humans, we want to, as operators, we want to make sure that we're not overdosing. Nothing worse than coming in and knowing that your chlorine pump was stuck in full auto all night and then having to make a phone call. So, having one of those is vital if you are a bigger facility. Obviously, on some of your smaller facilities, you're not going to have that luxury. But, I always recommend that, um, you know, you take more chlorine samples than you're required to take from the EPA. So when chlorine comes, it can come on 622. It can come in cylinders, cylinders containing 150 pounds. They are convenient um, for small plants, and we want to keep these in the upright position. So that is a test question. Sometimes is you want to keep the cylinders in an upright position. The ton tanks you want to keep on their side, and the reason why is you can roll them, and they have fusible plugs that will rupture if the chlorine gas gets too strong, and that's true in your cylinders and your ton tanks. But if you keep it on your side, then you can roll it so that it can escape as liquid and not gas. You can see a chlorine tank car on page 627. Another test question I've seen in the past, that's not saying they're always there, but on page 626, you don't want to use wrenches longer than 6 inches. The reason why is because you could force something and break it. So with 6 inches, you just don't have that leverage that you would normally have. Um, to find a chlorine leak on page 629, to find a small chlorine leak, tie a rag on a stick. Dip the rag in a strong ammonia solution and hold the rag near the selected points. Um, eh, that's how you test for a leak with ammonia. And what you're looking for, I believe, is a white smoke. If one of you guys in the comment section want to say 100%, but you're looking for a white smoke. So when you put that ammonia rag over the small leak, you'll see a white smoke, and then you'll know where it is. And so that, once again, I've seen it several times on a test. Hypochlorite. These are the liquid feeding type. On page 633, you have a hypochlorite solution. Sometimes that's be like 12% typically that gets delivered to your plant. If you have a real small plant, possibly you're using 5.5 that you just, you know, got from somewhere. But as you can see, you have a day tank that's usually mixed up, and then a pump, and the pump pumps it into a pipe. And usually at that pipe, then it'll go into a tank where you have the contact. And we'll go into that for coring to work, we it has to have time. And it's a temperature dependent thing and a time dependent. Let's talk about dechlor. You know, so we've chlorinated our wastewater. We've destroyed any pathogens in there, E. coli or fecal. We've destroyed any of those. Now we want to take that chlorine back out before we discharge it through uh, the receiving waters. And so you have products like sodium sulfite, um, and that is a tablet dechlorination unit. And as you can see, the flow flows through those tablets. And as that bottom tablet dissolves, the next one pops down. It sounds good in theory. Maybe you've had more success with these, but they have a tendency to get gummed up in the bottom, and that bottom one doesn't completely dissolve, and then the next one. And for small plants, it may be okay, but my personal preference, like I said before, is UV. But you know, another thing that we can feed is, well, one, I need to um, say that an overdose of sodium sulfite can have a negative effect on dissolved oxygen and the effect on the pH. So we really need to watch that we don't overfeed our dechlor. The next would be sulfur dioxide. Sulfur dioxide is a colorless gas with a characteristic pungent odor. The gas may be cooled and compressed to a colorless liquid. As with chlorine, when the chlorine dioxide is in a closed container, the liquid and gas normally are in equilibrium. So you can use sodium dioxide to to take out the chlorine out of your wastewater system. Once again, all these systems, you need to read your SDS sheets. Make sure that you're determining the correct residual amount of sodium dioxide in your system. And just as an operator, it's your keen eye, just making sure everything sounds good, looks good, because it is obviously a chemical that we are discharging. Let's talk about ultraviolet radiation. Beyond the visible light spectrum, there is a band of electromagnetic, commonly called ultraviolet light, in spite of being invisible to the human eyes. Um, Unlike chlorine disinfection, UV disinfection is mainly a physical process. The radiation is thought to disrupt the genetic material of the microbes, which makes them unable to grow or reproduce. And that is a test question I've had several times. So it doesn't necessarily destroy them. It prohibits their ability to reproduce. UV dose equals UV intensity plus the time. So the slower the water is moving past that UV light, typically the the better disinfection that you're going to have. UV light, though, is dependent on how many solids you have in your stream. So let's put the influent. Like obviously, you couldn't shoot UV light on the influent; it wouldn't disinfect because the light particles are going to scatter over whatever is in the water. And so those particles are going to pick up the light and it's going to scatter it and it's going to protect some of those um, E. coli or fecal from getting um, zapped by the UV. One thing when we talk about UV, um, we're right into that 200 to 300 nm. And, you want to, even though we see UV when we go out in the sun, if you can see my face, I'm kind of red. You know, we don't want to look at that light. And so there are specially made goggles for us to work on that light. Usually there will be a bulb that goes down into the water. The light will actually go inside the sleeve. I'm sorry, a sleeve will go into the water and the bulb will enter into the sleeve and the water will pass by that sleeve. It's a clear sleeve. And that's the basis of UV disinfection. This on page 664, that's a good picture of a UV rack. You have to be really careful with them. I've bumped them and broken a few. But every year we take them out, we rebuild them. It may be a ballast, it may be a bad sensor, it might be a bad bulb. The sleeve may break. The sleeves may be fouled on the outside because of dirt, debris, and so we have to wash those. They make some that automatically clean themselves. Others, you have to hand clean them. But you can see the UV radiation emitted by a tube. So you have your lamp, you have your particles, and your pathogen. So this is in an open channel on page 666. So you have an open channel where it will disinfect, but UV bulbs can also be in a closed channel in a pipe. And so you can disinfect a closed vessel UV, which is pic, picted, pictorial in figure 7.35. You could probably use that in one of the smaller plants, run it through um, um, a pipe with one of those connected. You may have critical sensors on yours that tell you when they need to clean. Some of ours are the ones I work with are, they have some of the technology, but as technology grows, you know, the UV system can get more and more complicated. Ozonation. Ozone is an alternative treatment process for disinfecting wastewater. Ozone is produced when oxygen molecules are exposed to an energy source and converted to an unstable gas. ozone, which is used for disinfection. Ozone is a very strong oxidant and viricide. Ozone is generated on site because it is unstable, decomposes to elemental oxygen in a short time after generation. High voltage electricity is used to generate ozone and disinfect water. I'm going to guess that most of you don't have ozone or will work with ozone, but let's look at some of the advantages of it. Ozone is more effective than chlorine in destroying viruses and bacteria. It uses a shorter contact time, and there are no harmful residuals. The disadvantage is uh, it's a complex technology, it's very reactive, and corrosive, and it is generally not economical for wastewater with high levels of suspended solids. Has a high capital cost and also has a high power cost. So that's the deal with Ozone Nation. Maybe as things improve, we will get another disinfection method. But that concludes chapter 7. Thank you.